Hello, this is a second video in a multi-part video series on Chapter 0 regarding the direct stiffness method. This video is a part of the final element class in Universidad de los Andes in Chile. A previous video regards the setup of the problem we're dealing with, which is a basic setup of the direct stiffness method. In this video, we're going to continue on what comes next. So, in the previous video, we set up the assembly process where we came up with the Ku equals F global system of stiffness equations. That is the relationship between the displacement degrees of freedom at the nodes and the right-hand side vector. We come up with a stiffness matrix which looks like this. There's a factor of times 10 to the 6 in all these numbers. And this is what we get at the end of the assembly process. Now, what you'll find is that what you want to do is k to the minus 1 of f, so that is inverting this system, so we can get the displacements, the degrees of freedom, or the solution of the problem. But you'll find that this system is not invertible. And the reason for that is that we have not included yet anything regarding the boundary conditions of the problem. That is, we have no fixities. Therefore, this is basically a body in space with no attachment whatsoever to Earth. Now, we did set up a table of restrictions in the previous slide, and it looks something like what we're seeing on screen right now, where we had at node 0, both the 0 and 1 degrees of freedom restrained with DOF values of 0, and at node number 2, we had the 0 fixity in the y direction. That is, on this degree of freedom vector, we know the red, green, and orange components to be 0. But what we don't know is for every restriction we have, we are going to have these reaction forces. So basically, we have at node number 0, we have a reaction 0 and we have a reaction 1. And we can add those two to on an unknown force called x0 and an unknown force in the vertical direction x1. And the same we can do at node number 2. We can have this f5 and r5. This one is unknown. This f5 will be known, which is forces that comes from either the nodes or the elements. But this one is a reaction force which is unknown at the setup of the problem. So we just lump all of those into this x unknown force. So basically we have two types of unknowns. We have the regular displacement unknowns, which are the blue degree of freedom variables, and some of the degrees of freedom are known. And to those degrees of freedom which are known, there are corresponding reaction forces which are unknown, which are these x. All the brown f variables, those are known. Basically coming from, again, the weight of self-weight of the elements, or the directly applied nodal forces. In this case, we had, if you remember, a vertical load of 4 in the number 4, of 100 kilonewtons in the number 4 node. So once we recognize that we do have some degrees of freedom which are known, we can set up a partition of the system in the following way. So we isolate the columns or the rows that correspond to the known degrees of freedom. We isolate the columns that correspond to those known degrees of freedom, and we basically reorder the whole matrix system so that we get at the bottom of the system the degree of freedom vector. We have the known degrees of freedom, and the unknown degrees of freedom, the blue ones, are on the top. And that partitions our system in that following way. So basically we have a sector of the matrix which corresponds solely to the unknown degrees of freedom, a mixed sector or a coupling sector, and then another block which corresponds to the known degrees of freedom. Basically we have a subset of the global degree of freedom vector which is free degrees of freedom, and another one which are constrained degrees of freedom, that is, those are known. And we partition this system like so. So if we read from the top system of equations, we get kff times uf plus kfc times uc. Uc is a known vector, equals ff. And the bottom equation reads kcf times uf plus kcc times uc equals xc. On this side we have unknown forces, and on this side we have unknown degrees of freedom. So basically, once we do that partitioning from the first equation, we can get the values of the unknown degrees of freedom by inverting this matrix. This is a fully invertible matrix, whereas the full matrix before was not invertible. We just do this product where we have the known degrees of freedom times the KFC matrix, and we come up with equivalent forces on the right hand side. And after we're done with that, this KFF matrix is usually not inverted. You use a Gaussian elimination process to do it for a large system. Inverting the matrix is not a good idea because it's a very costly process, whereas the Gaussian elimination is much more efficient. But once we're done with that, if we're interested in these reaction forces, so remember the reaction forces are part of what makes the right hand side vector. If we're interested in those, we can solve them from this equation. So xc is equal to rc, the reaction forces, plus the known nodal equivalent forces, which is equal to kcf uf plus kcc uc. And since uf is known from the previous equation, we can just dump it in here, subtract fc, which is another known vector, to get the reaction forces. So that's what we see there in the equation. And that's all that involves the solution process. Just as a recap, when we formed the global system of equations, we have not yet put any boundary conditions, so this matrix is not invertible. This system of equations is not solvable. We add the restrictions, we add the constraints by partitioning the system and identifying the known degree of freedom values and the unknown reaction forces that come from those known degree of freedom values. And we solve the partitioned system. From the top system, we get the degree of freedom values. From the bottom system, if we want, we can get the reaction forces. And that's all that entails the solution of the system of equations. Of course, this setup is for a static problem. We will deal with dynamic problems in further lessons. Thank you.